distinguished seminar speaker, Professor Venu Viruvale today. So Professor Viruvale received his PhD degree from electrical engineering from University of Illinois at Urbana-Champaign, where he is currently the Henry Smagnuski Professor in the ECE department. And he also holds appointment with the Coordinated Science Laboratory and the Department of Statistics. Before joining UIUC, he also had appointment at Cornell University. He also served as a program director at NSF for a couple of years. So Professor Viruvale has a very broad research interest that spans over the theoretical areas of statistical inference, machine learning, and information theory, with applications to data science, wireless communications, and sensor networks. So he is a fellow of IEEE, and Professor Viruvale has won a lot of prestigious awards. So among them, he has won IEEE Brother J. Thompson Best Paper Award and the very prestigious Presidential Early Career Award, which was known as PCAS, and also the Abraham Wald Prize in Sequential Analysis. Very recently, he has received a Fulbright Naupia Distinguished Chair in Information and Communication Technologies. So I was very fortunate that I did my PhD with Professor Viruvale, so from whom I learned many amazing things that are very beneficial to my career as well. So without further ado, Professor Viruvale will talk about his recent work on principled out-of-distribution detection in machine learning. Yeah.
Thank you, Min. And I was very fortunate, of course, to have Yingmin as my graduate student. And I think she was one of my first students to make it to the academia and have a wonderful career. So I'm very fortunate. So this talk is about out of distribution detection and machine learning, and this joint work with one of my current PhD students, Akshaya Magesh, who's going to be on the job market next year. So she's very bright. Same league as Yingmin. And two other co-authors on this work are Susmit Jha and Anupam Roy, who are at SRI, and this is we're part of a large project at the University of Illinois on called the Internet of Battlefield Things, being supported by ARM. Okay. All right. Let's see if this works. It's supposed to work. Maybe batteries have run out or okay. Okay, so let's see. I really do want the clicker to work. So unless you have another clicker, I can use the keyboard, but maybe I can steam the batteries. Oh, even that. Oh, the keyboard's not working. The keyboard is. Sorry about that. Let me see if this works. Yeah, that's better. There we go. Okay. Yeah, this batteries were out, I guess. All right. So let me motivate the problem. Why we want to do out of distribution detection. So this is a lot of you know about this tragedy that happened in 2018 with a Waymo self-driving car in Arizona. So the car was trying to the machine learning algorithm, the AI system in the car, was trying to figure out what it was seeing and through the camera, and so this is actually from an article in Wired magazine where they interviewed the operator of the vehicle, and so she described what happened. So the ML algorithm for a little while thought what it was seeing was another vehicle, but it's actually a person with a bike, but moving the bike, and not on the bike, but actually moving as a pedestrian with the bike with them. So that confused the algorithm because it wasn't the classes it had in its data set, its training out and its training data set. So it waffled between calling it a vehicle, a bicycle, and something it categorized as other. By other meaning that it didn't have confidence for any of the categories it knew that that image should correspond to. And eventually, of course, it was too late by the time it decided that it was something that needed to be avoided. And we all know what happened. So if the point is that if the ML algorithm were able to detect that input was something that it shouldn't have given a class for, something which we're going to call out of distribution, then maybe it could have taken a safe action, like just stopping the car, right? So in safety critical applications like this, or medical applications, I think it's important for machine learning algorithms to know when they won't be able to go do a good job with an input. Okay, in that case, you take a safe action. Okay, so that's the motivation. So what's this? So where does this come from? So machine learning algorithms are generally trained to generalize well to inputs from the training distribution. Okay, and so if you're given an input corresponding to one of the classes it's trained on, it can actually produce that class with high confidence. That's a good thing. Problem is that you can also produce incorrect class predictions with high confidence. That's a problem. Okay, if it was low confidence, maybe you could have used that to say, well, this is something I shouldn't be classifying. The problem is you can have something that really doesn't belong, right, to this in any of the classes that it had been trained on, irrelevant inputs. They don't have a corresponding class, but still produce high confidence output. So let me give you some examples, right? So here's a ResNet 34 that's been trained on a CFAR10 data set, which has 10 classes, airplane, automobile, and so on, to truck. And here are some examples from those classes. So in distribution examples, this is an image of a truck, and it actually, this is the softmax score. It's like a measure of confidence of the output. So it's saying it's a truck with this score, very close to 1, right? So it's doing a good job with that. It's doing a good job with bird, automobile, horse, and ship. The problem is that I can give it a picture from a different data set, right? This is numbers, take pictures of numbers of street houses, right? Taken from a car driving along the street. And so you have images like this. So this was classified as a bird, not a very high confidence score, but still pretty high for the softmax output, right? With 10 classes, that's a pretty high number. And this thing is classified as a cat, right? That is a deer, not very high confidence. But you have some of these numbers are pretty high. That number 8 was classified as a cat. Okay, same thing happens if I take a different set of inputs from a different set of pictures. And this is from LSUN, which corresponds to large scale scene understanding, and classes are things like bedroom, bridge, kitchen, and so on. And here again, this was classified as frog, that as bird, with very high confidence, right? And that was again frog, and then again, so pretty high confidence numbers. So if again our Waymo system, okay, had confidence numbers like that, it could have classified it as something that was benign, and then that could lead to problems. So let's try and define this problem formally. Machine learning problem with input output pair XY, which to come from some distribution. And you have training data for that distribution. Okay. And then you develop a model, F, which maps the input to an output estimate, and the parameters of the model are obtained from the training data using one of the standard algorithms. Okay, so the goal in OOD detection at a high level is to use to do OOD detection, you need to be given something, because all you're going to have is the machine learning model and the input, and you want to know whether that input is out of distribution or not. So in order to be able to do a good job, you need a little more information. And what we're going to assume, and what we typically assume, is that we have a small set of labeled data, which could be a subset of the training data. And I'll call that the calibration data set. Okay, so given that, the model, we need to determine whether the new input, X test, will produce a trustworthy output. And if you think the output is not going to be trustworthy, we're going to call that OOD, right? So that's the problem. The thing is that the untrustworthy output might be produced due to two reasons, two primary reasons. First is that the input may not conform to the training data distribution. Okay, so it may be completely outside the support, for example, of the training data distribution, in which case it's easy to tell, maybe, but there are lots of methods to tell that it's out of distribution. But actually, more importantly, untrustworthy outputs might be due to the fact that the model, based on the training data it had, wasn't really able to capture the relationship between the X test and its true label. And the true label could be, of course, outside the class of labels that are seen in the training data. Okay. So, and we need to do this detection without any prior exposure to OOD input, and should be applicable to any pre-trained model. So one could always say, well, suppose I took my model and then created a class called other, right? And then I just threw a bunch of pictures, right? A bunch of images. For example, if we looked at the CFAR10 example, if I just threw a whole bunch of pictures from a totally random set of data sets and created a category called other, right? What's the problem with doing that? The problem with doing that is that the OOD, there's no limit on what OOD could be. So this set will be so huge that it will start dominating the output of the classifier, right? So you can't do that. So you can't, that approach really won't work. So you have to assume that you don't know what it's going to see. It's to be just based on that X test and nothing else. So there's been a lot of work on this problem over the last few years. And primarily that work has been on constructing heuristic statistics, right, for detecting an OOD sample, and then thresholding to say if it's OOD or not. Okay. There's a bunch of examples of these. Okay, there may be a lot more than this. Actually, some of the early work was this OODIN work that came out of University of Illinois. And again, the point I want to make is that these statistics were developed empirically, just by seeing, playing with things, taking transformations of outputs from the neural network, and then and seeing whether they were empirically whether they were able to tell with confidence whether an input really out of distribution or not, but not with any principled justification. And that's going to be the point of my talk, that I'm going to try and give what I think is a principled justification for developing a good OOD detection algorithm. So here's some examples of things that have been used in this picture here. So I have a neural network with a few layers. So one of the metrics that has been popular is just to take the softmax layer. This is right before you make a class decision, and do some create some kind of energy score from that softmax layer, And empirically, it turns out that the in distribution samples have a small score, and out of distribution samples tend to have a large score. So you could use that as a measure, as a way to detect out of distributions. There are other things you could do. This Mahalanobis approach is to look at the output of a given layer, say layer 3 in this case, and compute its empirical mean on the training data and covariance matrix on the training data, and then look at the deviation, the Mahalanobis deviation of the input for the test input X. You look at the layer output and then compute this Mahalanobis score and see whether it's large or not. If it's large, then corresponds to out of distribution. Things like that. There's also another way to do this, to look at what's called a Graham score, which again, you look at some deviation from what would happen on the training data, right? So let's see. So first of all, I want to see if using these scores to create statistics to do out of distribution text, can it be justified formally in some sense? So for that, we go to think about OOD detection. Really, it's a hypothesis testing problem. So let's think about it that way, right? So one way to think about it formally is to say, well, in distribution corresponds to the X coming from P of X, which is the input distribution, right? Out of distribution is anything that's outside that doesn't belong to P of X. The problem with this is that this doesn't say anything about this is really outlier detection in input space. It doesn't care about the machine learning algorithm. It doesn't care about the output. Okay, it can work in some situations, but not in most interesting situations where that erroneous classification was really a problem with the classifier and how it interacted with the input. Not with just the fact that the input is. It's also hard to say that you could have inputs, especially with images. The input space is so large, just to actually conclude that the input is out of distribution might be a difficult thing to do. Okay. So an improved formulation is somehow to include the output, right? So you can say, let's look at the input and the output, the true output, okay? Not the one produced by the algorithm. If it comes from the joint distribution of the input and the output that would have been produced by the machine learning algorithms for that input, right? Then we call it in distribution, and otherwise we say it's out of distribution. Well, it's nice, right? So this involves both the input distribution and the model, because the model comes in through y hat. Okay, so we could do this. The problem is we don't know y test, because this is the true label corresponding to X, right? All we have is the label that's produced by the machine learning algorithm. So we have y hat. So we can replace y test with y hat test. We also don't know the true distribution of X and y hat. Right? So we'll replace that with the empirical distribution based on the training data. But if we did this, and you have a good neural network for which the training error is going to be close to 0, then y and y hat are going to be almost equal to each other for almost all the training data points. In this case, the empirical distribution, the joint empirical distribution between X and y hat is the same as the joint distribution between X and Y. Right? Because X and Y and y hat basically are going to be the same for every point in the training data set. So then the hypothesis testing problem, which would be X test and y hat test, and seeing whether it belongs to P hat becomes P hat of XY. But P hat of XY doesn't involve the training model. I mean, it doesn't involve the machine learning model. It's just looking at the joint distribution of the input and the output, the true output. So again, this is not going to work very well. Right? So that's the point I'm making here. So this hypothesis test will not involve the machine learning model except through that one sample y-hat test. So in order to get something interesting, an interesting hypothesis testing problem from which we can construct good OOD detection methods, we need to use functions other than just the output y. Output y-hat of the machine learning model. Okay, and that's why things like this work really well. If you just use the output, you couldn't do much. But if you use other statistics like Mahalanobis scores, Gram matrices, all of these were developed without much theoretical justification. But what our hypothesis testing formulation is saying is that we really have to have those in order to get an effective test for OOD detection. Right? So basically, our framework provides a theoretical basis for using such scores, other than just the output machine learning. But what I'm going to convince you, hopefully, at the end of this talk, is that this way of thinking about the problem will also lead to a systematic way to combine scores that you can get by various methods to get a robust solution that works in a broad range of situations for the OOD. Okay, so what I'm saying is that you're going to create all these other functions. Let's call them G1, G2, GK, and call the corresponding outputs of those functions ZI. So the ZIs are some vector valued functions. They could be, say, the outputs of layers of your neural network, which I showed earlier. And you can take the ZIs then to, say, form a one-dimensional statistic, which I'll call a score, and what I'll call a score function. And I can then compare that to a threshold. Right? So the hypothesis testing problem now is to look at the joint distribution of all of these and see whether it corresponds to all of these come from in distribution or not. Right? Well, of course, we don't know the P's, so we're going to replace these P's with P hat. So you could do that. But there's two issues with this formulation. So this, theoretically, you should be able to do something with this. The two issues with formulation is that this P hat is a joint distribution of all of these variables, and these are all high dimensional quantities. It's very difficult to accurately estimate this from the training data for the purposes of constructing a good detection statistic. But if you somehow you say, well, I'm going to just combine them in some ad hoc manner. I'll add them up, or I'll first form a score and then take some function and then add them up. And you can try these out empirically. But if you do that, you may not be able to control the false alarm rate of the test or give any guarantees. Right? Or you might result in a test whose detection performance is poor in some situations. It really depends. You're not really estimating the joint distribution well, so you're not going to get a good way to combine these statistics either. So this is where thinking about this problem not as just one binary hypothesis test, but to think of it as really as multiple testing actually plays a role. That this will allow us to combine things across these different ZIs. Okay. Okay, so we can think of in distribution. Let's take them one by one. So there's the ZIs are separated out into K hypotheses, and H0 corresponds to being an in distribution with respect to each of the ZIs, and H1 corresponds to being out of distribution. Now, a particular X test will be is said to be overall in distribution, globally in distribution, if H0I is true for all I, which also corresponds to the global hypothesis H0 being true. Okay, that's what will be in distribution. But if any of these other alternate hypotheses were true, that would correspond to out of distribution. Or any of the H0I is rejected and one of those accepted, then we have an out of distribution. The advantage of thinking about this problem this way is that one can use p-values to construct powerful tests to combine these statistics and also give strong false alarm guarantees, theoretically justified false alarm guarantees. Yeah.
So if those Z1 up to ZK, if those are generated by a neural network,
Yeah.
then those are just deterministic functions of the input.
Yeah.
Then the joint distribution will be basically just determined by the input.
Right. So just like even that, you could say that about the output y hat as well, right? In fact, one of these guys could be y hat as well. So the randomness there is coming from the training data. And that's what the joint distribution of these things will be determined by. Okay, that's a good question. So I know that, how many of you have seen p-values? Yeah, so so p-values are typically taught in statistics courses on statistical inference, but not so much in ECE. The textbook that I wrote with Pierre Moulin, we do spend 3 pages on p-values and multiple testing, but very little. I think that we should spend more time on it. So I'm going to, give you a very brief introduction to why p-values are useful for hypothesis testing. So you have a T, let's think of T now as a scalar test statistic for testing between two hypotheses, H0 and H1, and corresponding distributions of P0 and P1. So the T is chosen in such a way that it's large under H1 and small under H0. For example, it could be a monotonic function of the likelihood ratio, right? So your decision rule would be of the form: reject H0 or accept H1 if T is bigger than eta, accept H0 otherwise. So this reject H0 terminology really comes from the statistical literature. So I kept that. Instead of calling it accept H1, I'll call it reject H0. Because we, again, for our problem, the reason why we're sticking with H0 in all of this is because we only have information about H0. We don't have anything about H1. So the p-value of a realization, little t, of our statistic capital T, is just the right tail of the distribution of T. Or it's 1 minus, it's the complementary CDF evaluated at T. Again, assuming for the purpose of this talk is that T has a continuous distribution, can be extended. Things get a little messier, but you can extend this idea to allow for more general distributions. Assume that, and for the purpose of our OOD problem, assuming that T is continuous is fine. So now this is a number, realization corresponding to little t. But now, if you vary that little t and think of that as a random variable capital T, you get a random quantity Q here. Q is something which I'll use Q for p-value so as to not confuse the p that I use for probability with p for p-value. So used a different symbol. So that Q is now a random variable between 0 and 1, right? And the nice thing about it is that, a nice property that Q has is that it's uniform under P0, and this is not hard to see. So in some undergraduate course on probability, you know that in order to simulate a random variable, one way to do that is to use the inverse CDF. And so we know that so you take start with the uniform, apply inverse CDF to it, you get the distribution you get a sample from the distribution of the random variable. This is going the other way around, right? And so if you apply the CDF to T, you get something that's uniformly distributed. So that holds under H0. And of course, under the alternate distribution, you're going to get something other than uniform. And under the alternate distribution, this will have a value that's skewed towards 0 because T will take larger values. So the p-value corresponding to that statistic under H1 will tend to have smaller values. So it'll be concentrated around 0 or skewed towards 0. Not necessarily concentrated, but it'll be skewed towards 0 under P1. So having a p-value close to 0 might be strong evidence against H0. Right? But again, one should not confuse the p-value with the posterior. It doesn't say anything about the posterior of H0, right? Because all you're using is the information conditioned on H0 being true in order to construct the p-value, right? So it doesn't tell me anything about the posterior. And so a large p-value is not necessarily evidence in favor of H0. It can happen due to two reasons. One is that H0 was true. The other is my test is not very good. My T is not very good at distinguishing between H0 and H1. Or the power is small. Okay, keep that in mind. All right. So what does that have to do with constructing tests for binary hypothesis testing? So this is our decision rule, comparing T to a threshold. And so the probability of false alarm for this decision rule is given by this, right? 1 minus F0 eta. And so if I want to meet a constraint PF less than alpha, okay, false alarm constraint of alpha, then the smallest threshold I can get away with is the F0 inverse 1 minus alpha. But in that case, comparing T to that threshold is the same as comparing Q to alpha. So I can rewrite this test in terms of the Q value, the P value, or Q value, since I use symbol Q, as if the P value is less than alpha, I accept H1 or reject H0, otherwise I accept H0. And it also follows from the fact that Q has a uniform distribution under H0, that the probability of this happening is equal to alpha, which is what I wanted to do. So it's another way of looking at this test, right? Just compare the P value. And one advantage of using this form rather than this is that typically when we study this in engineering classes, we just are worried about whether, we just care about whether we have decided hypothesis H0 or H1, and then we stop there. But the p-value gives you a little more information. You might have set it to meet a false alarm constraint of 0.1, but if your p-value is 0.01, rather, very far away from the threshold, then you can be more confident that your decision is correct. So what happens in the multiple testing case? Things get more interesting in the multiple testing case. So if I want to test between multiple binary hypotheses, and each of them, I have a statistic for that and corresponding p-values. And the goal of multiple testing is to jointly control performance across the k-test. If I was going to control the performance of each individual test, then I wouldn't need to do multiple testing. I know how to do that, right? So it's only because I have some joint performance I'm worried about. So one of the things you could do is you could ask for what's called the minimizing, controlling the family-wise error rate. So family-wise error rate is the probability of falsely rejecting at least one null hypothesis. So, one of these null hypotheses was true, and then I chose the alternate. Okay, if at least one of those things happens, I put that in the event of that corresponds to FWR. There's another way to measure performance, which is slightly less conservative. It's called the false discovery rate. So here we look at the number of tests that rejected the null hypothesis among all k-tests. And among these, we see which ones are the true null hypotheses among these ones that are being rejected. So that ratio is something less than 1, less than or equal to 1. And we look at the expected value of that ratio under the condition, of course, that the number of tests that reject the null hypothesis is bigger than or equal to 1. If it's equal to 0, it is not relevant. So these measures make sense? Okay. So first, let's look at a very simple procedure to control the family-wise error rate. So we can let EI be the event that the ith null hypothesis is falsely rejected, and E be the family-wise error event, at least one null hypothesis falsely rejected. By the union bound, this probability of this, which is FWER, is upper bounded by the sum of the PIs, but each of those PIs is just the false alarm probability or false alarm rate for the individual tests. So I could control that by making sure that each of those tests, each of those p-values is upper bounded by alpha divided by k, if k is the number of tests. If I do that, then by the union bound, the FWER will be then upper bounded by alpha. So I can control the family-wise error rate by choosing this test. And this procedure is called the Bonferroni procedure. Okay. What about the FDR instead? So there's another procedure called the Benjamini-Hochberg procedure, named after the people who came up with it. In this case, you order the p-values, right? So with the Q1 being Q superscript bracket 1 being the smallest. And here you reject the first M hypotheses for which the QI is strictly less than alpha I divided by this constant here. So let me just, so what is this thing here? So in Bonferroni, we compare each of these Qs to alpha over K. In B edge, you're making these larger by the factor I, which corresponds to the index of the ordered values. And then you're dividing it by some CK. And it turns out that the CK can be just chosen to be 1 if the statistics are independent or satisfy what's called the PRDC, or positive correlation condition, okay, which is actually pretty hard to check except in very special cases. So think of this as being useful mostly in the case where the statistics are independent, but for our problem, actually, the statistics are not going to be independent. They're all derived from the same neural network. So if there's dependency, you need to add this, put this CK down here. Right? And this procedure controls the FDR at level alpha. Okay. So both of these are candidate procedures we could use for our problem. But we're actually interested in a very special case of this multiple testing problem. As I mentioned earlier, we're interested in the case where in distribution corresponds to all the H0s being true. Okay. So in this case, if you look at the FDR metric, R is the number of tests that reject null hypotheses, but V is going to equal R because all of the rejected null hypotheses are true because everything is true in this case. So the probability of falsely rejecting at least one null hypothesis is just the same as the probability that R is bigger than or equal to 1. What about the FDR? FDR has this ratio, but this ratio is 1, right? And so it just becomes the indicator function that R is bigger than or equal to 1, which is also the same thing. So in this special case, the family-wise error rate and FDR are exactly the same thing. And both of them equal the probability of rejecting H0 under H0, the global null. And so that's the probability of false alarm. Good. So I could use either of these procedures Bonferroni or BH, so for my problem. So which one should I choose? Well, it turns out that this one is quite conservative because I need all the Q values to be below this alpha over K threshold in order to reject them. So in order to detect that is being over D. Whereas this procedure, right, these constants will generally tend to be larger. For small values of I, the CK is of the order of log K. So these constants could be larger than alpha over K, but smaller than alpha over K. But for most reasonable values, it's going to be larger. And again, you're comparing the smaller p-values with the smaller constants. So so in most settings, this is going to have a better power because it's more likely to classify something as H1 than this test. So both of them will actually manage to keep the false alarm rate at alpha, again, without knowing anything about the dependency structure, but the BH procedure generally has better power. Okay. So that's, so we want to use this for our testing, right? But there's another problem with applying this method to OLD detection, and that is that we don't have the p-values. We don't know the distribution on the H0. So what could we do then? Well, this is where the calibration set plays a role, right? Suppose we have a set of empirical samples of the statistic. And for example, so if we set aside some of the training data, right? And we could use those and look at what statistics would have been produced by the calibration data set by my model. Right? So now I have T1 through Tn as empirical samples of T. Right? So then all I do is replace the p-value with its estimated value from the data. It's just a frequentist version of the p-value, right? Except I've done a little bit of smoothing here. I added a 1 to the numerator and denominator so that this estimate is never 0. The beautiful thing about this is that this p-value estimated this way, right? If I look at its CDF condition on the calibration data. So this is the CDF of the p-value, probably that the conformal p-value is less than alpha. Conditional data. This is a random quantity, right? Random quantity between 0 and 1. And that random quantity can be shown to have a beta distribution. This is for all n, not just in the limit. It doesn't require any concentration. Right? So you can completely characterize this. Okay. And of course, as n goes to infinity, this beta distribution will concentrate to alpha. Why? Because the mean of the beta distribution is the ratio of A to A plus B, and that ratio will go to alpha as n goes to infinity, and the variance can be shown to go to 0 as 1 over n. So this thing concentrates to alpha, a deterministic quantity, alpha, as n goes to infinity. So what that is saying is that this conformal p-value for large n also has a uniform distribution under H0. Okay. But more importantly, we actually know something about the conditional distribution of this for any TCal. And that conditional distribution is not a function of the elements of TCal, but only on the number. Okay. Right. So now let's talk about how we use all of this, putting everything together. So you have these multiple tests. you form statistics, right? These statistics are formed by taking some function of the x and the zi's, right? And we call this function Si as a score function, right? And that could, for example, be the Mahalanobis distance score obtained from some inner layer of the neural network. Using our calibration data set, we form these conformal p-values, rank them, and if any one of them exceeds, is smaller than its threshold, any one of them is smaller than threshold, then one of those hypotheses has said that the alternate is true. We say OD is true. So that's the procedure.
May I ask a question? This is Emre Koksal. I'm joining from Zoom.
Yeah.
So it's a naive question. So in the previous slide, for example, so you have these different sequences of functions, right? I mean, it's G1, G2, whatever.
Yeah.
So if you look at, for example, the value of G2, if I'm looking at the PDF of value of G2, given the value of G1 and X test, I would think that it's an impulse, right? It would be impulsive because let's assume the functions are one-to-one and on-to. So if you construct
it's not an impulse because there is still randomness in the weights that comes from the training data, right? So it's not a deterministic function. Yeah.
Yeah,
if it was a deterministic function, it wouldn't be useful. Right?
Yeah, that's where I was going, because I assume that like the X test, the marginal distribution is the same for
no, it's different because the weights are random.
I see.
It's random. It's really the randomness comes from the training data. Yeah.
All right. Okay. Thanks. That clarifies the question. Thanks.
Actually, similar to what Yingmin asked earlier. So what kind of guarantees can we give? And this is the real nice thing. So this and the result I talked about earlier, this concentration, this not concentration, but this beta distribution result is going to play a key role in being able to provide strong theoretical guarantees on the false alarm rate. So what we can say is that we can find a size for the calibration. Again, and remember that the beta distribution only depends on the size, not on the actual samples. Right? So one can determine a size for that calibration data set that will say that with probability 1 minus delta, given a delta, right? So measure of confidence there. I can say that with probability 1 minus delta, my false alarm for my test is upper bounded by alpha, as long as my calibration data set is large enough. And how large does it need to be, right? So one can actually find a complicated equation relating these quantities using that beta function, beta distribution. Okay. And you can plot it numerically. So this is the plot of the calibration data size versus delta. I think this was for K, the number of tests equal to 10. And alpha, in this case, let's look at alpha equal to 0.05 first. So the number of points you need to say guarantee for a delta, say of say 0.1 is around 5,000. But if you go down, say to even 0.01, somewhere there, it doesn't shoot up dramatically, maybe around 9,000 samples, enough to guarantee. And usually this is a conservative estimate of NCal that's needed. Okay, and alpha gets larger than the NCal needed is even smaller. Okay, and you can actually we verified this empirically to make sure that we do meet we stay below the upper bound, and so this is the upper bound calculated from our that we desire for alpha, and with the NCal chosen. We're using the graph on the previous slide, you can see that the alpha stays below that in all these cases. Sometimes it's overly conservative. Here it's fairly tight. This is ResNet. I think in ResNet it turns out to be tighter than the DenseNet. Okay, but still, we have a systematic way to choose the size of the calibration data set to guarantee that false alarm will be met with high probability. Okay, now this one, I think I need a little more room. Okay, there we go. So here's some experimental results. Okay, let's see what's the easiest way to describe it. So CFAR10, the one with those pictures of cats and deers or whatever, deer and all, that was the in distribution data set from the picture I showed earlier on. And we want the false alarm rate in this case to be at 10% or 0.1. And each entry here is the probability of detection, right, that we obtain empirically. I think we, to estimate the probability of detection, I think we used about somewhere between 10,000 and 20,000 samples out of distribution inputs. Okay. And so these are some prior methods that were known to work well for a certain, and this was reported in other papers on certain out of distribution data sets. In this case, SVHN, the one with the house numbers. Right. And we see that, in this case, the energy statistic does quite well. It gives you it tells you that it's out of distribution 96% of the time. But the other ones don't do as well. But our method, which combines these scores using your p-values, gives a much, it gives a score that's better than all. It's only marginally better than the best, but still it's better than all of them. And that is true throughout here. So if we look at examples in ImageNet, LSUN, again, there's one of these is doing pretty well, but ours is uniformly doing well in all cases. I don't know why I forgot to put the last one. It should have been in red as well. I forgot to put that in red, but it does uniformly better. So what this is able to do is kind of get the best out of all these statistics and come up with something that's robust and works well in a wide variety of situations. Okay, and some more examples on the next slide. Because these numbers will all get a little smaller if I make my alpha smaller, as we all know. Okay. All right, so that's it, and these are the conclusions. I can take questions while you stare at these if you like.
Questions?
Yeah.
Maybe a little more of a comment than a question. In this literature, it's been argued that the way that you're setting up the experiments where you have one data set versus another is not very useful in practice, because the things that distinguish data sets are often not meaningful, like there are little textural differences or something.
Yeah.
So a much more robust way to do a comparison, take something like CIFAR-10 and take out one class, think of that as the outliers, and think of the 9 remaining as the inliers, and then average that over all 10 classes.
Yeah.
And that's a much more difficult problem, but much more
Yeah,
meaningful.
probably all these numbers are going to be a lot smaller in that case. I don't know if it's more meaningful necessarily, but yeah, but
It's
most of the papers I've seen you use something like this for comparison.
I think when you look maybe at the theoretical literature, they're not going to be very
Oh, I
sophisticated,
see.
the experiments and vice versa. Right?
I see.
But like coming back to your motivating picture, with the self-driving cars, and if you think about things that way, if that's really your motivation,
Yeah, so the
Then
bike
it
or
matters.
the bike with the pedestrian is
exactly.
really like some combination of things.
It's like the one missing class that, there's all these things it knows about, but there's that one thing it doesn't know about.
But that was just for that case, right? It could have been something else for a different scenario, though. So how do you know what what you should be thinking of at OOD. If you knew that, then you would know the OOD class beforehand, and you would just train for the OOD class as well. So I'm not convinced by that argument.
I'll share the
necessarily,
papers
but
with you, but
I'm not necessarily convinced, but there may, I'm not claiming that this is the best way to test these algorithms, but I'm not also convinced that that is going to be any more meaningful necessarily. So, it might have been meaningful maybe for that one particular case, right? But it could have been something else in the environment that was completely different. That could have been classified with high probability as being one of those classes, right? That they knew too. So, and the other thing I've not talked about is what if an adversary was trying to create these these inputs? Then, of course, I think there may be ways to get around any scheme that we can dream of for detecting OOD. So I'm not really talking about that. So that's a separate set of problems, I think. Yeah. So this is more like it just comes from the environment. It's not being, it's not being created on purpose. So I suppose you could create really hard examples to do our OOD detection through some adversarial techniques. But is that the right thing to compare to test these algorithms on? I'm not convinced. I don't know. But is that what you're trying to say?
I think there's practical applications where you care about adversaries.
Yes.
And then in those
yes,
cases,
yes.
you're right, adversarial would be a good thing to worry about. But if you're not, then I would agree that adversarial is not an issue.
Yeah.
But if you care about having,
But
knowing about many things, but there being one thing that you don't know,
right.
then I do think that
Right.
this other method is more important.
But if there's one thing that you really care about, then and you know that beforehand, you would train for it. So.
Well, but again, you don't know. There's the thing, the
Okay.
unknown unknown, right? So,
Right.
so that's why you do this leave one out.
Right, that's-
And
Well-
Phil's experiment design removes the confound that there's some other aspect of the image database that is the tip-off, that is the distinguishing feature that makes it out of class in an obvious way. Maybe it's just an offset in the grayscale or a texture or a lighting condition or
Right.
a color scale that
Yeah,
sort of,
so
sort of
it's
the problem falls apart and you're testing an onion.
Sure, that could happen, yes,
Yeah.
that could happen. But in that case, okay, you do the best you can with that, or you create a bunch of candidate solutions and then use my method for combining them.
Yeah, I'm not criticizing your method at all. It's
Right.
really nice work.
So, as evidenced by some other questions, randomness in these PDFs that you list comes from the training set itself.
Right.
And I'm inviting you, if you would please say something about using a subset of that data, the same data, to then estimate distributions you're using for controlling false alarms. Does your theory say anything about benefit of having independence?
I mean, you don't really require it necessarily, because all you need is the calibration set to be independent of the test input in order for the theory to work. Right. But you're right. I mean, I think ideally you would want that calibration data set to be independent of the training data, not a subset of it. And it's small anyway. So it doesn't have to be very large, like what
Okay, but the theory is you've derived it is silent on that potential.
yeah, that's right.
Okay. Thank you.
So I think there is an
There's-
online question over here in the chat.
I'll look at it, yeah. Is there any book that states whether the OOD is learnable? You see that, you see it on the screen here. I have no idea, actually. Yeah, it's a good question, but Yingman probably can answer that better than I can.
Anna, do you want to specify a little bit what you mean by OOD is learnable? Do you mean the distribution of OOD data is learnable?
So yeah, so this is under high. Yeah, so my point is that is there any work which says that okay, if your data distribution is somewhat, I mean, under what conditions? Okay, so if you have some kind of OAD which is kind of learnable, for more example, more in the
Yeah.
line of supervised learning, we call about the PSC learning, right? Probably approximately whether is there some kind of guarantees there for the OAD?
Yeah, I don't know. It would be difficult, right? Because this OOD space is just
Too large.
too large.
Yeah.
Yeah, so
Is
that's
there-
why I thought about is there any condition, okay, with under what conditions, okay, this.
Right.
I mean,
Yeah.
if they all fall into one distribution, then certainly it's
Yeah.
learnable. But depending on, what
How
are the
complex it
data,
is, yeah.
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 Yeah. That might be actually also related to what Phil is saying is. Yeah. If you make it learnable, maybe these methods are going to be easier to develop, right? Under that assumption, I mean, yeah.
Hmm.
Yeah,
Yeah. Yeah, thanks. Yeah.
So I had this question about this parameter K you had. You selected to be some K.
oh, no, it's not a parameter, it's just that it's the number of.
Number of tests,
Statistics
sorry.
I'm combining.
Number of statistics. So I was curious about that number. So is it always advantageous to have more? Or is there a limit to how many, as the more you have, also you may need. that
Yeah,
would
and it's
affect
probably diminishing returns, I would think.
Right.
And also, you might know beforehand that some statistics are really bad, and you don't want to be combining with those because this is not like, okay, this is similar to boosting, but it's not like, not the same thing as boosting in the sense that there's no guarantee that combining these is going to give you better performance necessarily than leaving one of those out.
Yeah, that's exactly what I was.
Yeah, there's no
thinking.
guarantee. It can happen. Especially, we found that energy statistic was known to be really bad for, I think it was for, I don't know what the distribution was. But for, I think the archive paper, oh, I should probably have given them. Yeah, I'm gonna do this. This archive paper talks about that example in the appendix. So there's a case for which the energy statistic is really a horrible statistic, whereas the other ones were all good. And so when we combine the energy statistic in that case, we got worse performance.
That was one question I had. I wonder
But
whether
I
your
think the K
procedure.
actually corresponds to Z1 up to Z.
Yeah. So there could be multiple Mahalanobis scores,
Mhm.
and they could all correspond to a different value of the different
Okay.
component of the K.
Does your procedure help you or could provide means of eliminating some of these, like more in an adapt, not on pre-knowledge, but more on quantities you observe, you kind of select and like make the best of the.
Yeah, but you have to do that empirically. So that's a problem because all we can control is the false alarm rate. We really can't give you any guarantees about the probability of detection beforehand because we have no idea where the out of distribution samples are coming from.
As you collect these Q values or P values or.
Right, so you have to just do it empirically, just try out different things and you find that, okay, for this input distribution, and this statistic, all the OOD samples that I've tried, this performs really poorly, so I shouldn't be using it. Yeah, but if you have things that are working pretty well, then it appears that combining them using our method empirically performs well. Yeah. Yeah, I wish I could have, I wish we had a result like what they have for boosting that you will get better performance than any the individual test, but we can't really prove that. And I don't think it's true. And we have counter examples of that.
It's best for situations where you have already well known to be good cases and you combine
Yeah.
them effectively.
Yeah. Some reasonably good. So, but yeah, you can't take poor statistics and combine them with this method.
I had a question about so this works for like out of distribution detection. Would this also work for anomaly detection? If you or just somehow like, like have a bunch of normal videos and you have one where there's like a car accident or something, would you be able to say like, oh, this like clearly falls outside of,
No, so that problem, I would say, falls under the umbrella of outlier detection.
Okay.
So I don't know, yeah. Yeah, because you're just looking at the input in that case, right? And not how it interacts with the machine learning algorithm. Or are you? If,
I mean, like, I guess like if you were trying to detect,
yeah, so I think it's just that I'm feeling that should just be treated as an outlier detection problem in the input space rather than. So, yeah. So, and there are techniques for doing that. Actually, model of this distance is one of the things that's used there. Yeah.
Yeah. Any other questions from online audience? If not, let's thank the speaker again.
Right.